Hello everyone, I am Han Yingqiu from Institute of Data Science and Knowledge Engineering, School of Computer Science in Beijing Institute of Technology. In this session, we discuss in-memory computing, represented by Spark. The data processing system provides big data computing and processing capability, and an application development platform. From the perspective of computing architecture, the data processing system is divided into data algorithm layer, computing model layer, computing platform, and engine layer. Computing models are the way that different kinds of big data is processed in different scenarios, which include batch processing, stream computing, large-scale concurrent processing, MPP model for structured data, in-memory computing model, and data flow graph models. Let's look at the fifth computing model, in-memory computing model. In-memory computing, or in-memory computation, is the technique of running computer calculations entirely in computer memory, for example, in RAM. This term typically implies large-scale, complex calculation which required specialized system software to run the calculations on computers working together in a cluster. As a cluster, the computers pool together their RAM, so the calculation is essentially run across computers and leverage the collective RAM space of all the computers together. This term is mostly synonymous with the in-memory computing and in-memory processing, with perhaps a slightly nuanced difference, where in-memory computation is a specific type of task dealing with calculations that falls under the umbrella of in-memory computing. In-memory processing can be considered a different type of tasks that also falls under in-memory computing. How does in-memory computing work? In-memory computation works by eliminating all slow data accesses and relying exclusively on data stored in RAM. Overall computation performance is greatly improved by removing the latency commonly seen when accessing hard disk drives or SSDs. Software running on one or more computers manages the computation as well as the data in memory, and in the case of multiple computers, the software divides the computation into smaller tasks, which are distributed out to each computer to run in parallel. Speaking of in-memory computing model, we must talk about Spark. Spark was initially started by Mathai Zuhari at UC Berkeley's AMP Lab in 2009 and open-sourced in 2010. In 2013, donated to the Apache Software Foundation, and it became one of the most active open-source big data projects, top-level Apache project. Parallel processing framework based on the memory computing model. It can be built on the Hadoop platform and use HDFS file system to store the data. But a resilient distributed dataset architecture, RDD, is built on top of the file system for support efficient distributed memory computing. In 2013, Hadoop finished the task of sorting 100 terabyte data within 72 minutes. In November 2014, Spark founder Mathai Zuhari's company, Databricks, set a new world record in large-scale sorting using Spark. Spark sorting the 100 terabyte data within 21 minutes, just using 207 machines, which is 1/10 of the numbers of the machines that Hadoop used, and reduced the time from 72 minutes to 23 minutes, which is far more faster and more efficient than Hadoop. Apache Spark is an open-source, distributed processing system used for big data workload. It utilized in-memory caching and optimized query execution for fast queries against data of any size. Simply put, Spark is a fast and general engine for large-scale data processing. The fast part means that it is faster than previous approach to work with big data like classical MapReduce. The secret for being faster is that Spark runs on memory, RAM, and that makes the processing much faster than on disk drive. The general part means that it can be used for multiple things like running distributed cycle, creating data pipelines, ingesting data into a database, running machine learning algorithms, working with graphs or data streams, and much more. Resilient Distributed Database, RDD, which is a collection of elements partitioned across the nodes of the cluster that can be operated on in parallel. RDDs are created by starting with a file in the Hadoop file system or other Hadoop supporting file system or an existing Scala collection in the driver program and transforming it. There are only two kinds of operation of RDD, transformations and action. In transformations, data can be filtered, joined, mapped, reduced, but no calculation is executed. Only in action, the calculation can be done, and the value result can be generated. Users may also ask Spark to persist an RDD in memory, allowing it to be reused efficiently across parallel operation. Finally, RDDs can automatically recover from node failures. The transformation return value is still an RDD. It uses the chain core design pattern. After calculating one RDD, transform it into another RDD, and then this RDD can be converted again. This process is distributed. Action return value is not an RDD. It is either a normal collection of Scala or a value, or it is empty, and eventually it is returned to the driver program, or the RDD is written to the file system. Action is the return value returned to the driver or stored in a file. It is the transformation from RDD to result. And the transformation is the transformation from RDD to RDD. Only when the action is executed, the RDD will be calculated and generated, which is the root of the lazy execution of RDD. This diagram shows the topology of the RDD transformations and the lineage of the RDD transformations, which the execution should follow. Spark running progress is like this. The Spark architecture uses the master-slave node in distributed computing. Master is the node containing the master process in the corresponding cluster, and the slave is the node containing the worker process in the cluster. Master is the controller of the entire cluster and is responsible for the normal operation of the entire cluster. Worker is equivalent to a computing node, receiving commands from the master node and reporting status. Executor is responsible for task execution. Client as the user client, is responsible for submitting applications, and the driver is responsible for controlling one application execution. After the Spark cluster is deployed, it is necessary to start the master process and the worker process on the master node and the slave node respectively to control the entire cluster. During the execution of a Spark application, driver and worker are two important roles. The driver program is the starting point of application logic execution, responsible for job scheduling, that is the distribution of tasks. And multiple workers are used to manage computing nodes and create executor parallel processing tasks. In the execution phase, the driver serializes the file and jars of the task, and the task depend on and transfer them to the corresponding worker machine. At the same time, the executor processes the task of the corresponding data partition. Execution or task. Each program has its own. Different programs are isolated from each other. Task is multi-threaded in parallel. The cluster is transparent to Spark, as long as Spark can obtain related nodes and processes. Driver keeps communication with executor and cooperates in processing. Features of Spark include in-memory computation. PySpark provides provision of in-memory computation. Computed results are stored in distributed memory, RAM, instead of stable storage disk. It provides very fast computation. Lazy evolution. Transformation in PySpark RDDs is lazy. It doesn't compute the result immediately, means that execution does not start until an action is triggered. When we call some operation in RDD for transformation, it does not execute immediately. Lazy evolution plays an important role in saving calculation overhead. It provides the optimization by reducing the number of queries. Fault tolerant. RDD track data lineage information to reconstruct lost data automatically. If failure occurs in any partition of RDDs, then that partition can be recomputed from the original fault-tolerant input dataset to create it. Immutability. The created data can be retrieved anytime, but its value can't be changed. RDDs can only be created through deterministic operation. Partitioning. RDDs are the collections of various data items that are so huge in size. Because of its size, they cannot fit into a single node and must be partitioned across various nodes. Another feature is persistency. It is an optimization technique where we can save the result of RDD evaluation. It stores the intermediate result so that we can use it further if required. It reduces the computation complexity. Another feature is coarse-grained operation. The coarse-grained operation means that we can transform the whole dataset, but not individual element on the dataset. On the other hand, fine-grained means we can transform individual element on the dataset. Apache Spark Core. Apache Spark Core is the underlying general execution engine for the Spark platform that all other functionality is built upon. It provides in-memory computing and referencing data sets, in external storage system. Another component is Spark Cycle. Spark Cycle is Apache Spark's module for working with structured data. The interfaces offered by Spark Cycle provides Spark with more information about the structure of both the data and the computation being performed. Spark Streaming. This component allows Spark to process real-time streaming data. Data can be ingested from many sources like Kafka, Flume, and HDFS, Hadoop distributed file system. Then the data can be processed using complex algorithms and pushed out to file systems, database, and live dashboard. Another component is MLlib, Machine Learning Library. Apache Spark is equipped with a rich library known as MLlib. This library contains a wide array of machine learning algorithms, classification, regression, clustering, and collaborative filtering, and so on. It also includes other tools for constructing, evaluating, and tuning machine learning pipelines. All these functionalities help Spark scale out across a cluster. Another component is GraphX. Spark also comes with a library to manipulate graph database and perform computations called GraphX. GraphX unifies ETL, extract, transform, and load, ETL process, exploratory analysis, and iterative graph computation within a single system. Spark makes it easy to start working with distributed computing system. Through its core API, support for multiple language native libraries that enable easy streaming, machine learning, graph computing, and cycle. The Spark ecosystem offers some of the most extensive capabilities and features of any technology out there. Other third-party contributions also make using Spark much easier and versatile. Spark advantages include fast processing. Fast processing means the most important feature of Apache Spark that has made the big data world choose this technology over others is its speed. Big data is characterized by volume, variety, velocity, and veracity, which need to be processed at a higher speed. Spark contains RDD, Resilient Distributed Dataset, which saves time in reading and writing operations, allowing it to run almost 10 to 100 times faster than Hadoop. Another advantage is flexibility. Apache Spark supports multiple languages and allows the developer to write applications in Java, Scala, R, or Python. In memory computing, Spark stores data in RAM of servers, which allow quick access and in turn accelerate the speed of analytics. Real-time processing. Spark is able to process real-time streaming data, unlike MapReduce, which processes only stored data. Spark is able to process real-time data and is therefore able to produce instant outcome. Another advantage is better analytics. In contrast to MapReduce that include map and reduce function, Spark includes much more than that. Apache Spark consists of a rich set of cycle query, machine learning algorithms, complex analytics, etc. With all these functionalities, analytics can be performed in a better fashion with the help of Spark. Spark is the most popular open-source distributed computing engine for big data analysis. used by data engineers and data scientists alike in thousands of organizations worldwide. Spark is the industry standard analytic engine for big data processing and machine learning. Spark enables you to process data at lightning speed for both batch and stream workloads. Spark can run on Hadoop, MongoDB, Cassandra, Kubernetes, Yarn, or standalone, and it works with a wide range of data inputs and outputs. Apache Spark has seen immense growth over the past several years, becoming the most effective data processing and AI engine in enterprise today due to its speed, ease of use, and sophisticated analytics. However, the cost of Spark is high as it requires lots of RAM to run in memory. Spark unifies data and AI by simplifying data preparation at a massive scale across various sources. Moreover, it provides a consistent set of APIs for both data engineering and data science workload, along with seamless integration of popular libraries such as TensorFlow, PyTorch, R, and scikit-learn. In this session, we learned in-memory computing represented by Spark. Thank you for your attention. If you have any questions, feel free to contact me.